With the first of several discussions about the glass transition temperature. So we said that our non-crystalline amorphous polymers can be distinguished from semi-crystalline polymers based on this kind of long-range order. Another critical criteria that we use to distinguish, again, between amorphous and semi-crystalline polymers is essentially, actually for polymers in general, is this glass transition temperature, Tg. So non-crystalline amorphous polymers can be basically either in a rubbery or glassy state, depending on kind of the temperatures. But the key thing is we exist in an amorphous polymer. We have these polymers essentially that are highly interpenetrated and entangled Gaussian coils at high temperatures. So you could kind of basically above Tg. So when my temperature is greater than Tg, we look like this. We have this kind of Gaussian coils, highly interpenetrated, and basically the physical picture here is that the coils overlap with one another. So what we have, so that your separate coils will intertwine. So basically it looks like kind of spaghetti. That's always the typical picture for kind of above your Tg in the melt state, your kind of polymers. So in this highly interpenetrated state, no solvent. So again, when we say the melt, when I say the melt state, I don't mean that T is greater than Tn. No. In the melt state, we are looking at a basically a situation where we just have polymers and no solvent. So high interpenetrated state without solvent, the polymer will act as if it's unperturbed, i.e. in the melt state, as we kind of looked at previously, what do we say in the melt if we have no solvent? Well, we said that our alpha is equal to 1. We're in basically theta conditions. So in the highly penetrated, when T is greater than Tg, when we're in the melt state, polymers, no solvent, ignore those messages popping up there, the polymer is at theta conditions, and we could treat our chains ideally. This is really, really important because it makes them much easier to think about theoretically. But essentially, because those polymers are highly interpenetrated, the polymers in the melt are feeling some pressure due to the other polymers that overcomes this excluded volume effect. So again, a polymer chain has some magical excluded volume here. We know that our excluded volume is greater for alpha greater than 1. Our excluded volume is less than 0 for alpha less than 1. So our excluded volume is in this ideal state, B equals 0 for alpha equals 1, or in our theta solvent. So again, there's no solvent here, but they feel some pressure, and that pressure overcomes essentially these excluded volume effects, yielding an ideal state, i.e. an excluded volume of 0. So your polymer chain here, there's no excluded volume. So it's just polymers are, again, highly interpenetrated. So we can treat them ideally. So what is the glass transition temperature then? So we're dealing with the melt. We're dealing with these highly interpenetrated, highly interpenetrated polymers. But what is the glass transition temperature? So the glass transition temperature is the temperature at which a polymer transitions from a fluid-like state to a glassy state. You'll also hear the term basically rubbery. So rubbery, fluid-like state. You could also hear the term viscous-like state to a glassy state, kind of frozen state. So this is when T is greater than Tg. This is when T is less than Tg. So below that temperature, or you're kind of in a solid state, solid like a mechanic solid. So when we're dealing with the glass, we just need an amorphous material. So short range order lacks long range translation, but it's short range order, no long range translational order, but it lacks kind of the translational fluctuations associated with fluids. What does that mean? A fluid can kind of move collectively around, but when we're below our Tg, our polymers are essentially seem to be kind of frozen in state. There is obviously some fluctuations, but again, we can't move collectively. So it is like a solid, but with randomly positioned atoms rather than ordered ones like a crystal. So to identify like the physical origin of our glass transition temperature, we could think of it in two ways. First, you could kind of think of it in terms of increasing temperature or in terms of decreasing temperature. But essentially, the glass transition is a competition between the available thermal energy, kT, and the strength of these intermolecular interactions. So let's think in terms of increasing temperature first. So if I am increasing my temperature, I'm going to scroll down here. So I'm going to start to increase temperature. So the glass transition temperature is going to be the point where the thermal energy, where my KT, is sufficient to break my intermolecular bonds, enabling fluid or collective type motion. So when KT is greater than EIJ, I'm going to be above my TG. When KT is greater than excuse me, when KT is greater than epsilon IJ, i.e. my thermal fluctuation, my thermal energy, my kinetic energy, or basically the thermal energy is greater than your intermolecular interactions, then I behave again, rubbery or fluidy or more viscous. When this is occurring, I am greater than my temperature is greater than TG. And that enables this fluid-like motions. So right here. If we decrease temperature, so let's go ahead and take it from, if I'm going down in temperature, you could think of the glass transition as basically the point where the viscosity of the polymer becomes infinite, and we eliminate molecular motions. So here, as we decrease temperature, our KT was initially greater than epsilon IJ, and as our temperature decreases, there eventually becomes a point where they're equal, and all these kind of thermal fluctuations in our liquid and our more viscous type motion gets killed out, and we're left with basically a polymer that's now frozen in place. Our viscosity becomes infinite, i.e. like a solid. So it eliminates this kind of long-range molecular motion, and it's this collective molecular motion. So that's kind of the key aspect of this idea of the glass transition temperature. Either case, the key property is that in a glass, the rearrangement of atoms is hindered, and we're limiting the ability of a system to relax to equilibrium when a stress is applied. So we're going to actually take a brief derivation and look at this kind of characteristic relaxation time and how it relates to TG, polymers, glasses, and rubbery states in just a second, because that's one of the key aspects here. All right, so next time we'll have a nice relaxing video talking about relaxation. See you in the next one. Bye.